All right. Good evening. My name is Akshat Mishra, and this is day 4 of 30 days of machine learning. As we know, if anyone has watched even a small snippet of the first three videos, I made a machine learning model repo consisting of 30 days of models, all models different for each day. This repo was made as a way to practice and really evaluate one's machine learning skills. All of the problem statements are different, slowly advancing from basic Kaggle type of projects, going on to very ambiguous and advanced deep learning and transformer based applications as well. So, without wasting any time, we should go on to day 4, which is a Titanic survival problem statement, which we are solving using decision tree. First things first, we'll go on to the problem statement. So, it's pretty simple. We have got a bunch of passengers on the Titanic, and we have to predict whether they survive the Titanic or not. Now, this is basic machine learning, so it's pretty simple. This is going to be like a supervised machine learning model where there are labels present already. So I have been given a number of features, like old data and historic data. Based on that, I am asked to predict whether new customers, whether new passengers are going to survive or not. Okay. Survival, not survival, like live or die. So that is like two outcomes which are possible. So we can easily conclude that this is nothing but a binary classification problem, which means a 0 1 kind of a problem. Okay. So it's always good to keep such things in mind because that is how we approach the model that we could be using. So first things first, we use the dataset, train.csv dataset from Kaggle on Titanic data. I can show you the dataset right here. This is the dataset. It's a very small, very simple dataset, but the data science part of the pipeline was interesting. So I've covered everything. You can just, I can scroll, you can look at it. There are 891 92 samples right here. Okay, very interesting. And if you look at the data, it really governs the model very well. So this is what we have to predict, survive, whether the passenger survives or not, class, name, and all of these various features that we have. So what they have asked us is that use this historical data and predict whether or not a new passenger is going to survive or not. Very, very, very naive model to build, to be honest. So we move on forward. This is the pipeline that we're implementing. It might look different as there are a lot more things added compared to the previous problems, but it is basically the same pipeline. Both of the first two steps, they cover the data part, the EDA and the data loading. Don't worry, I'll be covering everything. Then this is the data pre-processing, all these three. Train test split, simple. Then decision tree training. I could have written model training here. We are using a decision tree here. I'll get to that as to why we are using that. Model evaluation. And I've added a visualization step to show how each and every split in the tree will be there. And feature importance analysis. Yeah, it's pretty important, pretty self-explanatory to be honest. So, since we have got on our hands a binary classification problem, a straightaway answer to solve this could have been logistic regression or a naive Bayes classifier because both of them are very intuitive when we have a binary classification problem on our hands. But I really wanted to, exploit the intuitiveness that comes along with Gini impurity in a decision tree model, which is why I've tried to implement it. You could also go ahead and try a logistic regression model. There's absolutely no issues with that. But this model here was pretty interesting to do. So let's dive into it. So first things first, I have done the EDA, which I'll be showing in the code. But first of all, I really wanted to just go around and play with the data set. So this is simple stuff. If I come to the code, import all the libraries and this typical again redundant from the previous videos. The two goats, NumPy and Panda, the two visualization libraries, sklearn until we go into deep learning. Everything is available in scikit-learn. Everything. This is how we fetch the data and yeah. Wait a second. Where are we? Just a second. I didn't copy the data before. I'll do it so that it is explanatory. Just a second. This is the EDA part. So if I copy it, I'll paste it in another one so that we can really explore it well. This is our original model. Okay, I'll delete this one. This is from the previous problem. Sorry. Yeah, fine now. So this is it, typical stuff. Standard scalar, again, I have imported it here, but it is not going to be used. One very simple conceptual remark here. So standard scalar, as I said, it is to bring our features to a comparable scale. Because, if in any formula-based models, distance-based models, or any model that involves using a numerical formula, what's going to happen is that the larger features are going to dominate and the results are going to be skewed and the model is not going to converge smoothly. We don't want that, which is why we use standard scalar in models such as that. But here on our hands, we have a decision tree model. The decision tree is rather based on, creating splits using a rule, which is either entropy or Gini impurity. So it doesn't really care about the feature scale, which is why there is actually no need of standard scalar here. But I just write it because, it's part of the typical sklearn steps. Select the model, decision tree classifier. This is how to implement it. Basic syntax stuff. You can look at it. Cross validation has been done. I'll be explaining that as well. These are the metrics, all of them. And this here is a new thing that I learned while building this model. This is to basically visualize the tree. I have included it later, but you can just look at it. So this is it. So this is the data set. I bring it here, copy the path, and this is the syntax to read the data, pd.read CSV. Now going into the EDA, we do simple stuff, You can look at the shape of the data, you can look at df.head, and you can get the first five rows, typical stuff. So I'll be going on to df.info. It is going to give me this information about all of the features in the data set. So there is no null values. Uh, Let me just check. Passenger ID, survive, it's typical. Okay, no null values in here. Then we go on to df.shape. What about the shape? So we go on to the shape. Let me just go on there. This will tell us how many rows and columns are there in the data. 891 by 12, simple as that. We can also count that here. So 12 means that these are 12 in number, and 891 means these rows that are scaling down. Okay, typical. Df.describe, it gives us the statistical information about the data set. Again, very old. So you get the count, mean, standard deviation. We did this in the last one as well. This is all very typical. That's it for the EDA. I don't think we have anything else because the model and the data was pretty straightforward. So this is it for the EDA, right? This is where we ended the EDA. And yeah, now comes the juice. Pay attention. Most important part of the model right here. The training is not big, the evaluation is not big. This is, according to me, the most important part, okay? Specifically in this model. So, when we look at the data pre-processing, okay, the first thing that comes to our mind is simple, very simple. What does come to our mind? Whether or not the model has missing values. Okay. Because if the data is missing values, we definitely need to fix it in order to, move on first. So what we do is let me just copy this so that I can, make this work in another code snippet. Yeah, this is it. Now, if I just go forward and run this, there we go. Okay, wait a second. Comment this part out. Yeah, got this. So as we can see, this is what's happening in here. Okay. These are our typical imports. And when we finally deal with the data set, so, this is how we check for the missing values. This is the simple syntax. No need to memorize the syntax. I mean, I didn't memorize it. You can get used to it once you write it too many times. But yeah, so df.isNull.sum, it will return the sum of missing values in a specific feature. What does that mean? Let's say in the passenger ID, there were five missing values. So it will return five in here. But there are no missing values in passenger ID. So we have zero. Okay. Now moving on, when we look at this, we can find missing values in age, in cabin, and in embark. Okay. So now what do we do? What's the next step? Handling the missing values. Very simple. Very simple. We'll go at this step by step, thinking very carefully. Okay. So how do we handle this? First of all, in these cases, you can sometimes go back to the data set to look as to how it looks like. So we go on to age and okay, value, 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 missing value, uh, missing value again, missing value again. This is, of course, there are missing values. This is just to look as to, how many missing values we are actually dealing with. So we can see there are some values missing. Okay, you go on to cabin. Look at this. Horrible, horrible feature, according to me. Why horrible? There is so much sparsity. See, there are 891 rows or 891 samples in this entire data set. And there are hardly 100 filled. Look at this. Okay. So upon seeing and calculating carefully, you can go and count as well using some Excel trick, but I'll just tell you the result. More than 70% values in the cabin column are missing values. More than 70%. So the basic instinct that comes to my mind specifically is to drop this column entirely. See, if the column is so sparse that it is adding only noise to a model, why should we even use it? There's no point. And cabin, since it's so sparse, it won't be used much in predicting whether or not the customer survived. So why should I use it? You can drop it straight away. Now that is a good instinct, but we have done something slightly more tricky here. So when you look at the cabin IDs, can you see this? C85, C123, E46. Now think of them like C, D, A, B. Think of them like the deck number. Okay. And think of 85, 123 like the seat number or the room number that has been assigned to the passenger in question. So, can we extract something out of cabin before throwing it away? What is salvageable in this cabin feature? That is what we have done. So, going back to the code, I'll explain what we have done. So we have made another column in the data set called as deck, which means the deck number or the deck ID, whatever. Okay. And deck is nothing but the first letter from the cabin. So as we can see in the cabin, we have got C85. So out of C85, C is going to be the deck number. Here we have C again as the deck number. So some passengers are going to have the deck number as common. And that gives us an interesting feature to explore. So we don't throw cabin straight away. We don't remove or drop the column straight away. First, we extract this useful feature out of it. Okay. So this is how we have extracted it. str0, which means the first index of the string, which means the first index out of the cabin number. We have extracted that and we have filled them up. Okay. This is what we have done. So this here right here was very important. Okay, this was the first time that I did that. That before throwing a column away, we took something useful out of the column and then like salvaged it. It's like it's like the Titanic is sinking. Okay, and I am on a lifeboat, and the ship captain asked me, grab the most important things and run. And I'm like, but that stuff doesn't belong to me. The captain is like, it is going to sink anyway. The boat is sinking anyway. Salvage and extract whatever useful you can out of it. That is the intuition. Okay. Because see, we were going to throw away this column anyway. Why not explore it first to see whether some useful feature is in it and then throw it away? Okay. So that is exactly what we did. Before throwing the cabin column away completely, by the way, we throw it off here. I am getting to that line. We first extract the deck out of it and then we throw it away. Okay. Now coming on to this pd.getDummies typical line in pandas, I'll explain it. What this does is basically it does the one hot encoding part, which means uh, we have got a column called as deck. So deck is going to have different values, right? We have got A, B, C, D. So it is going to build one hot encoding vectors for all of those deck values. And drop first is equal to true is very important if someone asks you. It's very basic. This is all very fundamental. It is used to avoid multicollinearity. Now, what does that mean? Now, let's say you've got three colors, red, blue, green. Okay. Now, if someone says to you that uh, their t-shirt is not colored red and it is not colored blue, then what it's going to be colored? Green. Simple as that. Okay. So basically, the point of this example is that we don't need all three features in order to have an idea as to what color we are dealing with. Okay. Because let's say that we have the survived column right here. Okay. Survived column. So survived, there is no -1.5 or 2, 3, any other values. This is a binary column, right? We have either survived or we have not survived. If I know that the passenger has survived, the not survived will definitely be having a value of 0. And if the passenger is not survived, then survived will definitely be having a value of 0. That is what we use here. So when we get these cabin numbers, C, then G, E, then A, D, if we know that the cabin number is A, the cabin name is A, then automatically B, C, D, E, F, all of that goes to 0 straight away. So do we need all the cabin names in order to know that? No, we don't. That is what drop first is equal to true takes care of. It's very important and very fundamental. Now, again, we do something so brutally naive, and it's brilliant, by the way. So you tell me something, does the name ever predict as to whether the person is going to die or not? No, no. I mean, if you think in some deeply connected way, then you might get an answer to that, but I don't think that the name is going to decide whether the person is going to survive or not. Okay. So we do what? We drop the name column completely. There is nothing useful in this column and nothing to extract from it. So we drop it completely. Okay. Does the passenger ID predict? No, the passenger ID is like the serial number. The serial number doesn't predict who's gonna survive and who's gonna not survive. So what do? We drop it. And the third one, the cabin, as we said that we extracted deck as the useful feature, we drop the cabin feature as well. Ticket, again, we go on here and we look at the ticket. This is the ticket. Okay. So I thought about the ticket as first because, it might be that the first class passengers survive and the third class, second, whatever class passengers, they have less chances of survival. But the ticket numbers are completely vague. Okay. Look at this. Stone 113. It's random. There is no pattern to extract from this. I understand that the first class and the third class example could be useful here, but there is no way because the ticket numbers are just they're very arbitrary, they're very random. We cannot extract anything out of this to prove that these passengers are from the first class or the third class. There is no classification in there. It's just going to add noise to the model, so we completely drop the ticket as well. Okay, so till now what have we done? Quick revision. We have dropped the useless column of cabin. We have extracted deck from it before dropping it, and we have dropped four other columns which were not predicting anything. Okay. Now, if you remember, we were getting missing values for two more things except cabin. So we have age and we have embark. These two are also having missing values. Now, the way to handle this, very theoretical idea, very simple idea. Okay. Let me go on to this again. There we go. So, first of all, embarked. It has only two missing values, which is fine, but we still need to address it. So, embarked, when we go into the column of embarked and look at how it looks like, this is what it looks like. Okay, it's like it has S, C, Q, and mixed values. This is the first one, by the way, the first missing value when we are looking at it. Okay, so how to deal with it? No, very simple. Whenever you deal with a feature like this, where most of the values are repeating, you see how many S are coming in here. So many S, then so many C's, so many Q's. There's just so much stuff coming out of the model here. So what we do is we replace the missing values with the most frequent values, which means the mode. Okay. The mode is the most frequent value. It's a basic statistical term. Out of mean, median, mode, this is the mode that we're using. This is how we, do it. This right here. Okay. So embark, the missing values are replaced with the mode. Simple. Now the age comes in. Okay. How are we gonna handle the age? Just a second. Handle age here. Okay. So how are we gonna handle the age? So the age again, you see, I could just take the average. Okay. I could take the average values and I could replace my age column with it. But there's an issue in that. What issue is that? You see, average or mean is a value which is very, very susceptible to outliers. Okay. It is basically the higher values or the values which are too large in number. Let's say there is a 70-year-old on Titanic and then there is a 5-year-old. So these values which are not in the middle, which are very high or very low, they basically harm the model. Okay, because they skew the results, right? If all values lie in the middle, we get a very smooth result. But if values are here and there, it's gonna just it's not going to make much sense because the larger values are going to dominate or the smaller values are going to diminish the mean too much. So rather than using mean here, we go and replace age with its median. Okay, with its median. Now, what is median? Median is nothing but the middle value. Okay, it's mathematical. You can calculate it if you want to. Median is nothing but the middle value in order to, deal with the missing values in the age column. Okay. So after that, basically our most of the pre-processing is done as we have handled the missing values. One very important thing we need to do is the encoding. So we have got only two types of genders in here. There are two types of genders, male and female in this. So again, the computer doesn't understand male or female. The algorithm doesn't. They just understand numbers. So we convert them to like a binary column. We can give female as 1 and we can give male automatically as 0 because it's a binary column. So that is exactly what we have done in this. This is called as feature encoding. Okay, feature encoding for categorical columns, which means there are categories here and we encode them by what? 0 and 1. It can be for multiple as well, but since we have only male and female here, we do it for 0 and this is typical again, df.get dummies. It is going to do the one hot encoding, but this time it is for the embarked column. And drop force is equal to true to avoid the multi-collinearity and the dummy variable trap. So this is basically it for for our pre-processing pipeline part. This is very typical. I've written this here. This was when I was building the model a few days back. You can read it. It's the same thing that we just talked about right now. So this is typical. Let me go back to the repo. See, this is it. This is again, you can read all of this. This is all that we have discussed right now. This is a bit different, explained well, because I don't, explain what I have already written. So you can read it up. Feature encoding, this is similar how it is done. Missing values. Okay. Feature encoding, again, the same thing, the embarked column that we handled. Okay. Now comes on the decision tree model. So decision tree, if someone is unfamiliar with it, decision tree is can be visualized like a tree. Okay. And there are basically splits created based on the feature values. And those values are dictated by a rule, rules actually, either the Gini impurity value or the entropy value. And by default, the decision tree model has Gini impurity to use to calculate the splits. Okay. First of all, independent and dependent variables. Let me show it once again. This is what we are predicting survive. Okay. And rest of these features, they are going to be used to predict whether the passenger in question has survived or not. So this is what we do. This is our dependent variable. This is our independent variables. We make the train test split, simple split, 80-20. Why 80-20? Because it is the most typical value. You can experiment with 70-30 as well, but since we have done cross validation here later, I haven't done it. Random state 42 gives us reproducible results. I've discussed this many times. Go on to the model, train it. This is it. Okay. Random state again here to produce reproducible results, and very important, max depth is equals to 4. Now, before this, we discussed the random forest classifier model. I think it was on day 3 or day 2, I guess. So, random forest is nothing but a collection or an ensemble of decision trees. Okay, you put one tree, another tree, another tree, another tree in parallel or in series, one after the other. That is what basically gives you a random forest model. This right here, decision tree, it is a standalone tree. It is individual right here. There are no other trees parallel or sequential to it. Okay. So these types of standalone models, most of the time, they have a very high risk of one thing, which is overfitting. Okay, what's going to happen is that this tree is, if we are not careful, this tree is going to memorize the data, and it will just give us horrible training accuracy. Okay, it will give us, no, it will give us horrible testing accuracy. Correction. It will give us a very high training accuracy, but a very low testing accuracy because it has memorized the training data. Okay. So we of course don't want that. We want to avoid both underfitting and we want to avoid both overfitting as well. We want somewhat like a low bias, low variance situation. So to avoid that, we have limited the max depth to 4. It could be some other value as well. This is basically, this is how your model building depth is checked. So you could have written 5, 3, whatever. You can try it out as well. But 4 here came out to be pretty good value. So we stuck with 4. You see, you can read this tree depth was limited. And decision trees, they, like I said, that they are kind of like black box models. They go deep, 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 deep. Splits are created at every step, and they are actually very strong in machine learning models. So they can memorize training data pretty quickly. And like I said, there are only 891 samples in this model, which is very low. So we have to be careful that the model is generalized and not favoring one side, which means that the bias is kind of absent. Okay. Then we go on to the cross validation part. Typical, very typical. Cross validation, as I mentioned, we have a 80-20 split, and we don't want the same values, the same 20% of values to be chosen every time when we are training the model. So cross validation basically divides the data set into five. So if there are 100 samples, it is going to be divided in 20, 20, 20, 20, 20, and it is going to pick a different set of 20% values every time. And in the end, it is going to average those values out to give us the appropriate results. To show this better, I have printed out the cross-validation scores. I'll be showing them in a second. Okay. These are some metrics I decided to print. I'll just be showing them. They're very interesting values. Uh, Syntax for the predictions. Metrics, since this is a classification problem, we get accuracy, precision, recall, F1 score, all of the usual stuff. By the way, this classification report function right here, it prints all of them at once. So you can use it as a shortcut. Accuracy, yes, it's an okay metric here. Confusion metrics will be showing us the true positive, false negative, and true negative values. Very good to interpret a model generalization capability. Visualization heat map, this is very good. Basically, the confusion matrix that we built here, I have visualized it using, a heat plot in the Seaborn library. I'll just be showing that. If you can go to the repo, you can see it right here as well. This is the confusion matrix that we got. Okay. So 1, 1, true positive, false positive kind of values. You can look at it. All right. Moving on, visualization. This is the tree. So again, like I said, that there was good visualization in this model. So I have decided to show the tree as to how the splits in the trees were created using Gini impurity. Okay. So you can look at this as well. This is right here. This is how the splits are created. So first of all, this is the original value that we were having. You see different feature names are written here. And then based on whether the passenger in question is surviving or not, two splits are created. Then more two splits are created, more splits are created. So this model gets pretty complicated, but the tree depth is limited to 1, 2, 3, 4 because we set max depth as 4. Okay. Simple feature importance. Which feature is the most important in predicting our model, in training our model? I have printed this here as well. See, feature importance is a very good graph to look at. So yeah, this is kind of kind of like a sad reality. So if you are a guy, you are most likely to die on shipwrecks or Titanic, wherever. If you are a guy, you're more likely to die. So here, sex, which means your gender, is the most important thing to decide whether the person is dying or not. Okay, they're very highly correlated. Passenger class is also pretty highly. Age again, then fare. Fare is, you know, fair is like an okayish metric here because maybe the model thinks that the higher fair means that the ticket is better. So maybe fair is used here for that, and the rest they're very weak to decide that. So feature importances are right here. This is it for the training of the model. If you can look at the code, you can maybe even make some changes according to how you like things. Okay. And coming on to the cross validation score, like I said, the scores will be calculated 5 times and then they will be averaged. So these are the 5 values calculated and then they're averaged out to get this value. Okay. I've also printed the standard deviation in order to get you an idea about the data. It's fine. Accuracy, we get about an 80% accuracy, which is fine. This is the classification report. F1 score, recall, precision. There are mathematical values that you can always explore. Okay. Confusion matrix, this is it. We printed it out in this beautiful heat plot as well. This is good to look at. True positive, 0, 0. Then we have got 0, 1. Okay. So 96 are the true positive values, which means that say the model predicted that 96 people are going to die. 96 people actually died. Okay. That is the no wait a second. Something's wrong. Yeah, no, that is it. So true positive, false positive, true negative, and false negative. Okay, typical. This is it. And if I go back to the repo, you can look at the formulas used as well. These are the mathematical concepts. So this is how the splits are created. It's either entropy or it's Gini impurity. So again, you know, Gini impurity is probability. One minus summation of probability squared. That is what we do in Gini impurity. This P here stands for probability. And this is a part of the CART algorithm. Basically, the algorithm that we implement is called as the CART algorithm. So this is less in terms of computation time as well. So this is the better thing to implement here. It's way more intuitive than entropy. And lower Gini impurity indicates nodes with a higher purity. So this is it. And let me just get on to the last part, which is the time complexity analysis. So you know how at every step we are creating splits in the tree according to the probability values. So which values will be used to create the splits? The lowest values. So to get the lowest values first, the model sorts these values. Okay. And sorting, as we know in any computation, means sorting in the best till now. And this is 7/5/2026. Till now, the best way it can be done is in end log n time. We have got the merge sort algorithm, which gives us, or maybe even the quick sort as well. We get n log n time complexity for all three cases, which means the best case, worst case, average case. So n log n for the sorting, and we are using f features for sorting at every step. So f for the number of features and sorting has got n log n, and we are sorting f times. So f multiplied by n log n is going to be the training or the time complexity of this specific model. Okay. Very intuitive, very easy to understand. And again, you need to have an idea how to calculate this. No need to memorize it because if you know what the model is doing, you can get it done. Space complexity, again, a simple fact that the tree stores a number of nodes. So if the tree has n nodes in the worst case, it will store them. And n is nothing but the height of the model. Okay. This is very typical. Yeah, I think this will be it for the model. If I miss something, I'll add it later. This is the code that you can access it. Thank you so much for watching this video. I will be coming back on for day 5, on which we have got a KNN model. Thank you.